Welcome to this comprehensive exploration of three fundamental machine learning concepts: epochs, batch size, and learning rate. These parameters control how your model learns from data and significantly impact training, performance, and final model quality. Understanding these concepts is crucial for anyone working with neural networks and machine learning algorithms. An epoch represents one complete pass through your entire training dataset. During each epoch, the model sees every training example once and updates its parameters accordingly. Multiple epochs allow the model to learn patterns progressively by seeing the same data multiple times from different perspectives. Here's a visual representation of a training dataset with 1000 samples. Each green circle represents one data point that our model needs to learn from. In one epoch, the model will process every single one of these samples. Watch as we simulate one epoch. The progress bar shows how much of the dataset has been processed. As the model goes through each sample, it learns and adjusts its parameters slightly. After completing one epoch, our model has seen every training sample exactly once. But typically, we need multiple epochs for the model to learn effectively. Let's see what happens across multiple epochs. In the second epoch, the model goes through the same data again, but now with updated parameters from the first epoch. This allows it to discover deeper patterns and improve its understanding of the data. Here's how epochs are implemented in practice. A typical training loop iterates through a specified number of epochs, processing the entire dataset in each iteration. This code shows a typical training loop. We iterate through the specified number of epochs. In each epoch, we process all batches from our data loader, which represents one complete pass through the dataset. After each epoch, we can evaluate the model's performance and track training progress. Choosing the right number of epochs is crucial. Too few epochs and your model underfits, it hasn't learned enough from the data. Too many epochs and it overfits, memorizing the training data instead of learning general patterns. Monitor validation loss to find the sweet spot, and consider early stopping to prevent overfitting. Batch size determines how many training samples are processed before the model updates its parameters. Instead of updating after every single sample, we group samples into batches for more efficient and stable training. This is both computationally efficient and often leads to better convergence. Here's a small dataset with 32 samples. Instead of processing one sample at a time, we'll divide this into batches. Let's see how different batch sizes affect the training process. With a batch size of 8, we divide our 32 samples into 4 batches. Each batch contains 8 samples, and the model will update its parameters 4 times per epoch, once after processing each batch. Watch as we process each batch sequentially. After each batch is processed, the model updates its parameters based on the gradients calculated from those 8 samples. Here's how different batch sizes affect training. Batch size 1 gives 32 updates per epoch with noisy but potentially faster convergence. Batch size 8 provides a good balance. Larger batches like 16 give more stable gradients and better GPU utilization. Full batch processing is most stable but may converge slowly or get stuck in local minima. Let's visualize how batch size affects the training process. We'll show gradient descent paths for different batch sizes to understand their impact on convergence. This loss landscape shows how different batch sizes affect the path to the optimal solution. The contour lines represent different loss levels, with the red dot being our target, the global minimum. Watch how different batch sizes create different convergence paths. Batch size 1 in yellow shows a very noisy, erratic path but can escape local minima. Batch size 8 in green shows a good balance of exploration and stability. Batch size 32 in blue shows a smooth, direct path but might get stuck in suboptimal solutions. Here's how to implement different batch sizes in practice using PyTorch's data loader. The batch size parameter controls how many samples are loaded together for processing. This code demonstrates how batch size affects training. We create data loaders with different batch sizes 16, 64, and 256. Notice how the number of batches per epoch changes inversely with batch size. Smaller batches mean more parameter updates per epoch, while larger batches mean fewer but more stable updates. Here's a summary of batch size trade-offs. Small batches use less memory but train slowly with noisy gradients. They can converge quickly but instably. Large batches need more memory and compute but provide stable gradients. Medium batches often provide the best balance for most applications. Learning rate is perhaps the most critical hyperparameter in machine learning. It controls how much the model's parameters change in response to the calculated error. Too high, and the model might overshoot the optimal solution. Too low, and training becomes painfully slow or gets stuck in local minima. Imagine a ball rolling down a hill toward the bottom. That's our model trying to find the minimum loss. The learning rate determines how big steps the ball takes as it rolls down. Let's start with a high learning rate of 0.8. Watch what happens. The ball takes huge steps and overshoots the minimum, bouncing back and forth without settling. Now let's try a medium learning rate of 0.1. The ball takes reasonable steps, steadily approaching the minimum without overshooting. This represents good, stable convergence. Finally, a low learning rate of 0.01. The ball takes tiny steps, moving very slowly toward the minimum. While it will eventually get there, training takes much longer. Let's visualize how different learning rates affect the training loss over time. This will show you the practical implications of your learning rate choice. Here are training loss curves for different learning rates. The yellow line shows a high learning rate. Notice the oscillations and instability. The green line shows an optimal learning rate with smooth, steady convergence. The orange line shows a low learning rate that converges slowly but steadily. In practice, we often use learning rate scheduling, starting with a higher learning rate and gradually reducing it during training. This combines the benefits of fast initial learning with stable fine-tuning toward the end. First, we import PyTorch and learning rate schedulers. Next, we set up a simple model and an Adam optimizer. Here are 4 common scheduling strategies: step learning rate, exponential decay, cosine annealing, and reduce on plateau. In the training loop, we update the learning rate each epoch. For plateau scheduling, we pass the loss to decide when to reduce the rate. Finally, we visualize how the learning rate evolves over time for each scheduling method. Now let's see how epochs, batch size, and learning rate work together in a complete training pipeline. Understanding their interactions is key to successful machine learning projects. We begin by importing PyTorch, schedulers, and matplotlib for visualization. The ML trainer class initializes datasets, model, optimizer, and a cosine learning rate scheduler. It also prepares lists to track metrics. The train one epoch method runs the forward pass, computes the loss, backpropagates, and updates weights batch by batch. The validate function evaluates performance on the validation set, computing both loss and accuracy. The training loop runs for multiple epochs, tracks metrics, updates the learning rate schedule, and prints progress. The plot training history method visualizes training and validation loss, learning rate schedule, batch size effects, and epoch progress. Finally, we create a dataset, define a model, and run experiments with different configurations of batch size, learning rate, and epochs. Let's establish practical guidelines for choosing these hyperparameters. These rules of thumb will help you get started, though the optimal values depend on your specific dataset and problem. Here are practical tuning guidelines. Start with proven defaults, Adam Optimizer. Batch size 64. Learning rate 0.001. Use a learning rate finder to identify the optimal range. Increase batch size if you have GPU memory. Always monitor both training and validation metrics. Use early stopping in systematic search, changing one parameter at a time initially. Mistake 1. Only monitoring training loss. This can hide overfitting, since validation loss may be increasing. The fix is simple. Track validation loss alongside training loss, and use early stopping to prevent overfitting. This ensures your model generalizes well. Mistake 2. Setting the learning rate too high. This often causes the loss to oscillate wildly or even explode. The solution. Start with a small learning rate, often 0.001, and use a scheduler such as cosine annealing. This stabilizes training and prevents divergence. Mistake 3. Using a very large batch size without adjusting the learning rate. This often slows convergence or undertrains the model. The solution. Apply the linear scaling rule. Scale the learning rate proportionally to the batch size. Mistake 4. Forgetting to shuffle the training data. This can introduce bias during training. The solution. Always shuffle your training data to ensure randomization and reduce training bias. Mistake 5. Stopping training too early with an arbitrary small epoch count. The fix. Use validation-based early stopping instead of arbitrary epoch counts. This ensures you stop at the optimal point. Mistake 6. Ignoring gradient clipping when using high learning rates. This can lead to exploding gradients. The solution. Apply gradient clipping. This prevents gradients from exploding and stabilizes training. Mistake 7. Training without logging or visualization. This leaves you blind to model performance. The solution. Use logging and visualization tools such as weights and biases or TensorBoard. They give real-time insight into your model's behavior. Let's conclude with a real-world example that demonstrates all concepts working together. We'll train an image classifier and see how our hyperparameter choices affect performance in practice. Here's what a real training session looks like. We're training on CIFAR10 with 64 samples per batch. Currently at epoch 47 of 100. The learning rate has been scheduled down to 0.0023. And we're seeing good convergence with 87.3% validation accuracy. The loss curve shows steady improvement with some natural oscillation. Here are real results from different hyperparameter configurations on CIFAR10. Conservative settings gave decent accuracy but took too long. Aggressive settings were fast but less accurate. The balanced approach with batch size 64. Learning rate 0.001, and cosine scheduling gave the best accuracy in reasonable time. This demonstrates why systematic experimentation is crucial. Let's summarize the key takeaways. Epochs represent complete passes through your data, use validation loss and early stopping to find the right number. Batch size affects memory, speed, and convergence. Start with 32 to 64 and scale up if possible. Learning rate is the most critical parameter. Start conservatively and use scheduling for better results. Remember, these parameters interact with each other. Here's practical advice for your machine learning journey. Start with proven defaults and experiment systematically. Always monitor both training and validation metrics to catch problems early. Log everything: metrics, hyperparameters, and observations. Use early stopping to prevent overfitting and save computational time. Most importantly, be patient. Good models take time and experimentation to develop properly. Your machine learning journey starts with understanding these fundamental concepts. Epochs, batch size, and learning rate are the building blocks of successful model training. Now you have the knowledge to make informed decisions about these hyperparameters and understand their impact on your models. Remember, every expert was once a beginner. Start with sensible defaults, experiment systematically, and don't be afraid to make mistakes. They're how you learn. The future of AI is built one epoch at a time, one batch at a time, one learning rate adjustment at a time. Your models are waiting to be trained. Thank you for joining this comprehensive exploration of epochs, batch size, and learning rate. These concepts form the foundation of successful machine learning. Practice with real datasets, experiment systematically, and remember that every expert was once a beginner. Your machine learning journey starts now. Go build amazing models.